Hello. Today I'll talk to you about distributional properties of subword regularization. However, maybe a better summary of this talk is more like uniformly sampling tokenizations is better than dropout. This was joint work with Willem Zohar and Naoaki Okazaki. Subword regularization is a technique that is especially common in low resource settings where we replace deterministic tokenizers with stochastic tokenizers that sample from a distribution of tokenizations. For example, the canonical tokenization of the word tokenization using something like BPE might be TO-KEN IZATION. However, many other possible tokenizations exist given the subword vocabulary. We want to sample from different possible tokenizations during training in order to break the reliance on a single canonical tokenization of a given input, regularize and improve the robustness of the model, and get some data augmentation for free. Subword regularization has been consistently shown to dramatically improve translation modeling quality. BPE and MaxMatch are popular subword tokenization schemes that have stochastic variants. These variants are basically just corruptions of the underlying deterministic tokenization process that injects some randomness and allows for sampling. However, if you inspect the distributions that they form, you can see that they are super biased towards just a few tokenizations. For example, out of all the possible tokenizations, sampling with BPE dropout returns the same tokenization more than 97% of the time. We also prove that this is an inherent property of these dropout schemes. Specifically, there are inputs for which MaxMatch and BPE dropout tokenization distributions are guaranteed to be biased. This paper came about because we thought that this extreme biasness meant that the aforementioned benefits of subword regularization were being artificially limited, and so the corresponding performance gains that we should expect are also being artificially limited. The biasness means that the model is exposed to fewer unique tokenizations during training, so it will still have a strong reliance on the canonical tokenization, and it will be less robust to different tokenizations, and it will have less unique data added as data augmentation. To fix this, we simply remove the stochastic elements of BPE and MaxMatch dropout and replace them with a uniform sampler built from a subword finite state transducer. Given an input, we produce a lattice that encodes all possible tokenizations of the input. Then, we sample a path uniformly at random from this lattice, giving a uniformly random tokenization of the input. This can be done efficiently and is provably a uniform sampler. Compared to BPE and MaxMatch dropout, uniform sampling exposes the model to the full range of possible tokenizations for any input word. In this chart, we see that even for very large sample sizes, BPE and MaxMatch dropout still don't eventually sample the full set of tokenizations for an input. On the other hand, uniform sampling samples the full set in a very small number of samples. On a series of translation tasks, we observed that uniform sampling consistently outperforms BPE and MaxMatch dropout on BLUE, CHRF, and COMET. It also outperforms UniGramLM on these metrics. In this specific translation task, uniform sampling improved the BLUE score over BPE dropout by nearly the same margin that BPE dropout improved over regular BPE. In conclusion, we proposed uniform sampling as an alternative to BPE and MaxMatch dropout in order to fix a theoretical flaw in their distributions. Uniform sampling demonstrated a consistent improvement in translation quality over BPE and MaxMatch dropout and UniGramLM. As future work, we are interested in variations of uniform sampling that have more desirable distributional properties. Additionally, we are interested in why both UniGramLM and uniform sampling work so well, despite them having opposing goals, as UniGramLM seeks to reduce entropy and uniform sampling seeks to maximize it. Thank you.